Okay, hello. Can y'all hear me? Okay, awesome. My name's Jeffro. Thank you guys for coming to my talk. I really appreciate it. I've been working on some Monero development for about 2 years, funded by the CCS. Very grateful for that. Yeah, I also did some stuff with a thing called Carrot, which is hopefully be an addressing protocol for Monero in the future. I worked on the Seraphis migration project, which is fun while it lasted. But yeah, I'm going to be talking about full chain membership proof plus and how it relates to SPV wallets. For y'all who don't know what an SPV wallet is, it's simplified payment verification. If you've ever used Monero, you probably know one of the most frustrating aspects sometimes is the amount of data you have to download to use a wallet, and just kind of like the UX around downloading the entire chain, verifying it, and then it's a heavy process. So simplified payment verification is a way to kind of cut that down. And there's some things that we can do at a protocol level to enable that kind of functionality to happen. So yeah, I'll just start talking about that a little bit. So a full wallet, a classical wallet, you'll download the entire blockchain, and then there's transactions on the blockchain. You verify the proofs for those. That can be heavy, but you have to download basically everything. You check everything, make sure it's all kosher and checks out. So, and then an SPV wallet, ideally, you only have to download the block headers. The block headers allows you to verify proof of work. The big assumption with SPV wallets is if the proof of work checks out, I'm just going to trust it. So with a full wallet, you don't trust the cryptographic proofs are correct. You actually verify them. With an SPV wallet, you just verify proof of work, and then you trust that the cryptographic proofs are okay if the proof of work checks out. So if you want to trick an SPV wallet, you've got to mine faster than the rest of the network combined. And in that case, a lot of the times, it's not even safe to accept payments anyways if you're a full wallet, because a transaction could check out cryptographically, but then get reorged out. Like I can say, I send you a transaction, but if I can mine faster than everyone else, I can just claw it back and take it back from you. So a lot of the times, it's not even safe if you're a full wallet if there's a 51% attack going on. So in that way, SPV wallets are almost as safe as full wallets, depending on what your requirements are. Yeah, and so SPV wallets, once you verify the headers, you can validate that some data belongs to the blockchain without actually having to download that. But how does that work? So I'm gonna try to give a really quick overview of like hash functions. Basically, a hash function, I use the meat grinder icon for a hash function. It's just a function that takes some objects, grinds them up, kind of like a meat grinder, kind of mangles them, and produces some kind of nice, neat output. And we need two major properties for these. Basically, what's called collision resistant is basically you can't put two things into the meat grinder and create the same output, and that it's not easy to guess what the output is going to be whenever you put something inside of it, unless you just do it. And then, so let's take a look at a block. This is a block. It's got transactions, and inside the transactions, you've got transaction outputs. If you want to give someone coins, you put them inside of a transaction output. So some people call them a coin. Well, what's cool about how Bitcoin does it and how Monero does it is that you can create a block content hash where you replace the actual contents of a block using a hash function. Just put the transaction list into the meat grinder, the hash function. You create a block content hash, and then from there, you can verify proof of work, or you can even mine if you wanted to do that. You don't actually need to know the contents of a block to step forward, mine, or validate proof of work. So, and what that allows you to do basically is the sender, it's kind of cut off on the edge there, but the sender, if they send you a payment, they can send you the payment, the transaction itself, and you can verify it as being inside of the chain by just reproducing the hash function. But can we do better? Can we, with SPV wallets and Monero, can we perhaps maybe validate zero conf transactions? Because if you're an SPV wallet, traditionally, you're going to need to download the blockchain, validate proof of work, and if you're doing zeroconf, you don't have that. So can we do that? And can we not depend on the daemon for data availability? So like, for example, right now, the daemon will send you information for the fees, which involves the transaction weights and the transaction weights of previous transactions and the fees that they paid. That helps you calculate what you think the fee should be. But if you don't trust the daemon, you can't trust that data. So now a crash course on full chain membership proofs plus, and I want to try to go through this pretty quickly. Aaron gave a pretty good basic, like a good foundation. So that was kind of nice that happened right before then. So you got our blockchain. We can put all this stuff in a line. Like Aaron mentioned, you can kind of create what's called a Merkle tree if you hash little groups of these together, and then you hash those results, and you hash those results, and you hash those results, and then you create a Merkle tree. So this is our tree root. Let's say, for example, I want to spend money. If I want to spend money, I have to prove that I actually have money. It exists on the chain. So let's say I wanted to convince a node that some coin actually exists on the chain. One thing that you can do is you create a Merkle tree, and I can take what's called the path, which is, if I'm talking about this transaction output right here, I take its parents and its parent siblings, their parents, their siblings, that parents, its siblings, that's parents, all the way until I get to the tree root. I just carve this path out, and then I can actually strip out the direct parents, and someone who is like the daemon who wants to validate this, wants to verify, they can just hash it together themselves. They can recreate the root, and then bam, I've proved that the coin exists in the chain and can commence sending money. So this isn't very private though. If I give you this data structure right here, if I give you this, I'm literally giving you a path to where my money is, and that's not very good for sender privacy, which we like in Monero. So we introduced something called Helioselene, and this is involved in a construction called curve trees. They have very special properties, which I'm trying to skip over for the sake of time. But basically, instead of hashing something directly, I can say that some element which I perform a transformation on, called a re-randomization, I transform it, and then I can prove that the transformed element, plus some other stuff, hashes into some output without actually revealing what it is. So instead of saying A, B, C hashes into X, I say some transformed value of A and a bunch of other stuff, which I'm not going to tell you, that hashes into X. And we can do that the same thing with the different curves. The collision resistance still applies, so I can't just like make up a value D, transform it, and say it goes into here. Otherwise, it'd be broken. So it has to actually have hashed into it. But if it did hash into it, you can say that thing transformed plus other stuff I'm not going to tell you, that goes into the output. But it has to have actually been hashed in. And then technically this runs in a bulletproof, and re-randomization is a Peterson commitment. And and then this has a nice property that you can do this to the transformed values, even if they're in the result. So if I put A, B, and C into this hash function, it creates an X value. I can re-randomize one of these elements. I can transform it into C. I can transform X into this little dotted X. And then I can prove that the transformed C hashes into the transformed X. And this allows us to do recursion, and some of you might be seeing where this is going. But we can, instead of a Merkle tree, we can make a curve tree, which is basically a Merkle tree, but with those cool properties. We can create paths, just like a Merkle tree. Carve out, I'm talking about this transaction output, create a path for that, just like you would with a Merkle tree. But now, because of those properties, we can flatten this path and re-randomize all the way down to where our transaction output is. We can say that some Selene layer hashes into the top, and then so on and so forth. Basically, we create a flat path that hides where the transaction output in the tree. The final goal of the whole full chain membership thing, if you don't get anything else out of this little section, is that this is the final goal. The final goal is to just prove that some transformed transaction output has a specific mathematical relationship with something that actually exists in the chain. So it's not something we like just made up. It's not, it's not an arbitrary transaction output. It's something that's transformed. It doesn't actually look like anything in the chain, but it has a specific relationship to something in the chain. That's the entire goal of full chain membership proofs. And then what about the plus plus? Wow, that's really small. But the rest of the plus plus is basically just saying that you know the private keys and that the key image is correct, which prevents infinite inflation. So herein lies the root of the problem for SPV wallets and just wallets who want to verify paths. Is how do they actually obtain these paths? Because we need the paths to be able to spend full chain membership proof plus plus money, but how do they actually get them? So option one is the simplest. Just download all of the transaction outputs from the entire chain. This is obviously not ideal because slow. You have to download the entire chain. So that's not a very great option. Another option is to download the paths directly from the daemon. So the daemon knows all the transaction outputs. It's already built the entire tree. It's already done the work. So you can just ask the daemon for that information. The problem with that is it's not very good for privacy, because if you're telling the daemon, I want this path for this output, and that reveals to the daemon that you are interested in that output, they might be able to guess that you own that money. So the second option would be do that same thing, but do it with decoys. So kind of like how we do with ring signatures, whenever we're asking for the daemon for information about how to spend money, we ask for a bunch of different transaction outputs, and then we make the ring signature locally. We typically ask for more than what we want, but that kind of gives some spend privacy from the daemon, because I could be spending this one, or I could be spending the other one. They can't really tell immediately. Still not great, but yeah, so the privacy is similar to ring signatures in that way. So option 4 would be to, did I skip over this? Oh, no, yeah, option 4 would be to download the path of the first, let's say your restore height is here. So maybe you own some stuff over here, but let's say your restore height is right here. If you've used a Monero wallet, you probably are familiar with the restore height. You have to put in a height value and specify where you want to start scanning on the chain. Because let's say, you've only been using Monero for, you're a newbie, you've been using it for 1 month. You don't need to scan since 2014. When people were talking about Thankful for Today on the Bitcoin forums. You don't need to scan all the way from back then to the present day. You can just scan from a month ago. So keeping that same technique in mind, let's say your restore height is right here. Maybe you own some coins in here. You can just download the path to where your restore height is, and then whenever you're scanning, you need to scan the rest of the outputs in the chain anyway. You can scan the rest of them. You can build the rest of the tree whenever you're doing your normal scanning, because if you know a little bit about Monero, the outputs, your addresses don't show up on the chain, so you need to scan it. You need to download all those anyways, so you can build the tree while you are doing the scanning. So that's one option. Fifth option is sort of an interesting option. This is kind of what, and this is kind of the technique that SPV wallets use, is where they'll send you all the information you need over an interactive channel. So if you're a Bitcoin SPV wallet, they'll send you the transaction itself, not just a reference to the transaction. They'll send you a transaction itself and the information you need to tie it into the block header. So that's basically what you can do here with Monero, is you can send the path you need to spend that money itself with the transaction as you're being notified of the payment. So that's you only need to download one path that way. So this is one of the more efficient ones, and you're not asking an untrusted daemon for any other information that you don't need. So pretty private. Has some downsides though. Doesn't work for zero payments because, again, if you're an SPV wallet, you need to be able to verify that something is on the chain. It also does not work. Interactive channels may. Let's say you have a ClearNet merchant over IPv4. You're over like the normal web. You might not want to be communicating directly with your customers, or it adds additional privacy risks if you have to have a channel open with them. and there's a bunch of other downsides, but. So option four is pretty good. Option 4 is pretty decent. Option 5 is okay. They both have, good spend privacy after a certain point. So it seems like the problem's solved, right? Except for this thing right here, the fake root attacks. How do we actually agree on a root? Because if we don't agree on our root, the daemon could just say, if you're downloading the initial path from the daemon, you can say, yeah, this is definitely what the tree looks like right now. This is the entire chain. The entire chain is just your transaction output. Now make a transaction. And if you do make a transaction, then they know for absolute sure that you actually do own this transaction output. And there's no way for you to say that the entire blockchain isn't just one output that you own. So if you successfully make a transaction after they give you something like this, and you can be a little more tricky. You can maybe send like 10 or whatever. You can fill it with fake data, but if the data is fake and you make a transaction, the daemon knows that you own that money, and they've basically doxed you. So that's how do we actually agree on what the tree root is? Because if we can agree on the tree root, like we said before with Merkle paths, if you can agree on the tree root, we can verify them. But how do we actually get that tree root? And one of the answers is just put it directly in the block data. This has the effect that if you try to fake it, if you try to modify the tree roots, it will invalidate all of the proof of work for all the blocks after it. And yeah, if you're an SPV wallet, you've verified proof of work, so you can tell that these are fake. Yeah, you validate them as appearing inside of the block. And because of the 10 block lock, we can actually know the blocks the roots 10 blocks in advance. So by the time you'd want to spend them, they already have 10 blocks worth of confirmations, which just makes it even more secure. It's actually 9 because specific detail. But if you see this, in the new block definition in the Monero code base, this might be the reasoning why it's there. And then so there's some other things we still have to work out. So we still have to verify that if we're going to do zero conf transaction verification, we need to know that key images have not been spent yet, because you can create a valid proof that some coin spends some transaction correctly, but how do you know that it hasn't already been spent correctly? This kind of has the opposite problem where you have to prove that something doesn't exist in a set. One of the ways to do this is called like an inclusion-exclusion proof. So you can order these things by value, not position in the chain. So previously, we were kind of lining them up in a line based on where they were in the chain. That makes it really easy to grow the tree. You can alternatively order these key images by value, and then you can give the path for 3 and 5. If 4 were to be in the set, it would go right there, but it's not. So the fact that you gave paths for both of those proves that it's not in the set. So you can do something like that, and then the roots of those trees would also go in the block. This is kind of speculative though. It gets pretty hairy because this tree has to balance, but it's ideas, food for thought. And then some other things we have to, like I previously mentioned, we have to take care of block weights, transaction fees, so we can calculate the fee and not have the daemon lie to us. Let's talk about header-only sync for a little bit. This one's pretty short, but this is just like an inefficiency of how the daemon is currently coded. We send what are called fluffy blocks whenever we want to sync the chain, but we don't need to. We could just send basically what the header and the block content hash, and that would allow us to do header-only sync without a hard fork. Doesn't require anything like that, but it would require a peer-to-peer protocol update. So that's just something that's kind of low-hanging fruit in the sense, yeah, it doesn't require any fork, require any kind of complicated consensus change. It would just be updating the node code. So that was cool. And then RandomX v2, Tevdor worked on this. So right now the RandomX is kind of heavy. You can kind of DOS people if you're really clever by just giving them a whole bunch of garbage input. And the fact that it's heavy to run RandomX itself, just to verify, not even to mine, just to verify, it's I think it might be 15 microseconds or 15 milliseconds. Anyway, I don't have the numbers on hand, but it's heavy. It's heavy comparative to say Blake to be or some kind of hash function. That's exactly what the fix for that would be, is you can feed the heavy hash function into a smaller hash function, and then if you want to verify just what's called the proof of work commitments, you can do that really, really quickly. And that was just a little thing that Tevdor came up with. Garbage input is a lot faster to sort through, so if you're worried about denial of service attacks on your wallet, this will help mitigate that a lot, because you have to mine to still get the proof of work commitments, but to initially filter out bad input, you can use a small hash function. So yeah, just putting it all together, introducing, full chain membership proof plus, maybe putting the tree roots and the block data, the RandomX changes, the changes to the peer-to-peer protocol. It's looking pretty good for future development for SPV wallets. It might be viable very soon, depending on different kind of development changes, but it's interesting to think about. So I don't know, and that's about all I've got. So thank you, appreciate it.
I think we've got time for a few questions, so start from the front.
Hi, if I understand it correctly, this curved tree stuff is basically a very efficient, succinct way of creating a zero-knowledge proof of something like the statement. This is a valid signature from one of the pub keys from among any output that has been previously created up to this point. Is that correct?
Yeah.
Yeah, that's very interesting, and it's a lot cheaper than if you were to do the naive thing and, like in a ZKVM or a generic ZKVM, prove a Merkle path, then prove the signature verification algorithm. I think that those two do the same thing, but the curved tree seems to be much more efficient, and the prover is probably smaller.
Yes. I don't have the numbers on hand. Yeah.
Yeah, but my real question is, are you or anyone else thinking about taking that same kind of idea and using that to create a kind of an analogously efficient and succinct way of doing something like an exclusion proof for a nullifier? So then you're proving both the signature validity and the lack of double-spendedness. Are you or anyone else that you're aware of thinking something along these lines?
So this is where my knowledge gets a little bit hazy. I'm pretty sure that's basically what Zcash does. I could be wrong. I might be, I might be wrong about this, but I think one of the things that Zcash does is they have their own version of basically an exclusion proof, and they have nullifiers, and in circuit they prove that the nullifier hasn't been seen before.
Yeah, but I think they are doing a more generic, straightforward thing, where you're proving the actual hashes of the Merkle tree inside the nullifier set. I could be wrong about that, but...
Yeah.
Okay, interesting. Well, if anyone wants to talk about this, we have an idea. I'd like to chat about this later. Thank you.
That's a good question, though. Thank you.
Another question.
From the miner's perspective, I'm wondering about the actual Merkle trees themselves. Is there going to be any cost for the amount of Merkle roots that they would verify? How many, how much time in the past do the miners have to constantly re-verify on that? What's the cost of going back in time and keeping an old Merkle root around?
So, yeah, that's a good... are you talking about additional costs to the miner versus just running a node?
Well, the miner will have to verify that the Merkle root that the transaction is proved on, if it's an old transaction, that it's still valid as of that point in time. It will have to discard it at some point. But how old can you get those transactions generated? And how much cost will there be for verifying that that upcoming transaction in the mempool is still valid with an old...
Okay, I think I see what you're saying. Yeah, building the tree is not that expensive. And so, okay, this is a really good question. I skipped over this for the sake of time, but
I can give you the time to actually do that because Seth is going to run short.
Okay.
So if you would like to cover that you skipped over because it's relevant, then please do it.
Okay. Yeah, that's a good question. Let me see. It's pretty far back there. Okay, so without trying to get too much into the weeds, building the tree is sort of expensive, but I mean, it's pretty cheap compared to verifying transactions, but it would actually, like if you're in the mempool, you know, you've got to know what the tree is for the inputs that are being spent. You don't have to know the tree value for the current outputs. And like, because we have the 10 block lock, you actually can know it 10 blocks in advance, and I skipped over this really quick, we switched to 9 because I think probably as you're thinking, as the transactions are coming in, if you want to calculate the Merkle tree for the transactions that are coming into the mempool that would be in the next block, that's going to change every single time, basically arbitrarily as new transactions come in. So if you had 100 transactions in the mempool, you've built like a little tree extension for 100 there's going to be at least 2 outputs, so like 200 outputs, say. And then the new one comes in, but it comes in at like basically a pseudo-random location. Like you can't really guess, because they're ordered based on where they would come up in the chain, which is basically random. It's not, like the miner doesn't get to decide it, basically, is what I'm trying to say. So the miner doesn't get to decide it, a new transaction comes in, and then you basically have to rebuild the whole tree for that block. So every single time there's an update, you have to build, so that's why we chose not to put the root in 10 blocks in advance, because technically they could know it, but it would probably cause a non-trivial amount of compute time, like thrashing basically. Every single time that mempool updated, you have to update the Merkle trees. But for just verifying consensus rules, so if we didn't have this at all, if we didn't put it in the, we didn't put the root inside of the block, and we're just worrying about verifying inputs, like you could build the tree with a 10 block lag. Like you wouldn't have to, as the outputs come in, you could actually wait 10 blocks to build the tree if all you care about is verification. So I don't know if that answered your question, but yeah, but we don't require the miners build the tree for the outputs that are in the block that they're mining, so they're not like thrashing, building different tree extensions as they're adding new transactions. That was a great question.
Great. Thank you so much, Jeffro. It's always a pleasure to have you here on our stage.
Thank you.